Okay. Okay. Good afternoon, all. Okay. From last few lectures, we are discussing related to the non-ferrous materials and their alloys. And in last lecture, we have, or in previous lectures, we have completed copper and copper alloys. Then after that, we have discussed about the aluminum and aluminum alloys. Now, in this lecture, we are going to discuss related to the age hardening process, or it is also known as the precipitation hardening process. In different examples, I think in the aluminum alloys or in the copper alloys also, you can see here in this example, this aluminum and copper alloys here, and copper and beryllium alloy. This is nothing but the beryllium bronze. Okay, and this is the aluminum copper alloy. Now, these whichever these two examples I have told you, these already we have discussed in the copper alloy. In the part this we have discussed in the beryllium bronze. This is nothing but the beryllium bronze material, and this is your aluminum and copper alloy. These will show the age hardening or precipitation hardening process. Just I have used this term, that is the precipitate due to the precipitation hardening, they will show the more hardness, or due to age hardening, they will show the more hardness. Now, what is the actual age hardening or precipitation hardening processes? Then what are its different types, or how why it occurs, and what are the conditions for occurring the precipitation hardening? There are generally two conditions which I have highlighted here. Two conditions are there, so that age hardening or precipitation hardening will take place in that particular alloy system. Then after that, general steps are there in the age hardening process. Generally three steps are there. Then artificial, there are two types of the hardening or aging processes are there, and how this aging processes, what are the factors affecting these aging processes, that I have highlighted here. Now, this part we are going to discuss in the today's lecture. Okay, as far as your examination is concerned, compulsory one question will be there on this age hardening process. Either they will ask you the basic concept along with its procedure, or the conditions for occurrence of the age hardening, or they will ask you the what are the different factors that will influence the kinetics, that is the speed of the aging process. What are the different factors that will influence the speed of this aging process? Or one write a short note question may be there for 7 marks. That time you have to explain all the part. In that you have to first start with the definition, that is what is the actual meaning of age hardening. Then you have to explain this is the actual meaning of the age hardening. Then conditions for occurrence of the age hardening or precipitation hardening. Two conditions you have to explain. After that, you have to explain general steps in the age hardening. And after explaining the general steps, you have to explain the factors affecting the kinetics of this aging process. Okay, that will be your detailed or brief answer for this. We will start with this first point, that is what is the meaning of the age hardening or precipitation hardening. Now, age hardening is nothing but whenever, suppose one alloy you have taken, we will consider this aluminum or copper alloy or this beryllium bronze alloy. Now, if you whenever you are using that alloy in the actual practice or in your practical work, as time passes away, if you take the readings, suppose I have taken one reading on the uh, today itself, that is 18th August, I have taken the reading of the hardness, and after interval of 15 days or 1 month, again I will take the reading of the hardness of that particular material or same alloy. Then at that time, suppose I will find at the end, you will find that the reading taken on the today's reading, and if you've taken two or three readings after a gap of 15 days or 20 days, you will find that as time is passing away, the hardness of that particular alloy is increasing. Okay, we are not performing any heat treatment or any other process on that particular alloy, but still, at that particular room temperature only, that alloy will show the increase in its hardness values. Okay, this process will be termed as the age hardening or precipitation hardening process. Okay, as I have highlighted here, this first point, alloy, some alloy will show increase in hardness with time at room temperature. Okay, all this phenomenon will occur at the room temperature only. Just as time is passing away, with the time they will show the increase in the hardness values. That process will be termed as the age hardening. Means just the age of that material or that alloy is increasing, which results in the increased hardness for that particular alloy. And sometimes, means whenever you are performing, suppose you are performing some artificial aging may be there. Sometimes with slight heating, we are not going to use very higher temperature values. With slight heating also, suppose 200 or 100 degrees Celsius temperature also, you are going to provide just slight heating, means raising the temperature by 100 or 200 degrees Celsius and cooling it. We are just doing the cooling it in the water. That will be termed, in this process also it will end up with the increased hardness. Okay, this process will be also termed as the age hardening or precipitation hardening. Okay, so this is the term or concept of the age hardening. Means some alloys will show the increase in the hardness value as time is passing away, and this all phenomenon will occur at the room temperature only. This is will be termed as the age hardening process. Sometimes some alloy will show the increase in the hardness value with slight heating and the one cooling operation. That will also termed as the age hardening, but it will come in the artificial aging, because we are doing artificial, means we are providing the external heat and all this. That's why it will be come in the artificial aging. One will be the natural aging, that is, um, as naturally time is passing away, there will be some increase in the hardness. This will be termed as the natural aging. And whenever you are providing some external heat with the suitable mediums, that will come under the artificial aging. Okay, so there are some example. This is the age hardening or precipitation hardening. Due to this aging processes, there will be some increase in the hardness. That's why it will be termed as age hardening and precipitation hardening process. Then the next is the some examples. You have to write some examples. Already I have explained that. Beryllium bronzes, that is copper with 2% beryllium. Copper with 2% beryllium, it will show the age hardening process. Then aluminum and copper alloys, aluminum with 4.5% copper. Here composition should be exact. Okay, at least these two examples are already you have discussed in the copper alloys and in the aluminum alloys, so that you can remember it easily. Some few examples I have added here. Aluminum with 6% zinc and 2.5% magnesium. Then nickel with 17% copper and 8% tin. And titanium with 6% aluminum and 4% vanadium. These are some examples. Now, after discussing what exact age hardening is, then we will move towards the what will be the conditions, or what conditions must be satisfied by that particular alloy system or that particular alloy to show the age hardening process or precipitation hardening process. There are two conditions. The first condition is the solubility limit. Solubility of solute. Okay, first condition will be related to the solubility limit, and in that it will be related to the solubility of the solute in the solvent. Okay, solubility of the solute. Here solute is nothing but your alloying element, and solvent is nothing but your parent element. Or if you take any example from this copper is the solvent, and this beryllium will be your solute. Means what is the condition here? Solubility of the solute in the solvent should decrease with decrease in the temperature. I will explain this with the help of this diagram. Here I have taken one general example. This curve. Okay, this curve, from this curve it is clear that whenever temperature is decreasing from equilibrium diagram, this is the general equilibrium diagram, or this type of curve should be there. This type of curve should be there. Means as temperature is decreasing, here you can say that as temperature is decreasing, solubility of the solute in the solvent is also decreasing. Okay, solubility of solute in the solvent is decreasing, that is the amount. The amount will decrease as temperature decreases, or in other words, as temperature is increasing, solubility should also increase. Okay, as temperature, whenever temperature is increasing here, its solubility will also increase. If this condition is satisfied by that particular alloy, then it may show the age hardening phenomenon. It may show, why I am using the term it may show, because it have to satisfy two conditions. This is the first condition. Okay, this is the first condition, that is solubility of the solute in the solvent must decrease with decrease in temperature, or must increase with increase in temperature. This is the first condition, and if it satisfies the first, there is probability that that alloy will show the age hardening process. But to show that, it must satisfy the second condition, and that second condition is that the precipitate that separates out from the matrix, it should be coherent. It precipitates, some particles will get separated during this process. Some particles will get separated, or new phases will be formed. Now here, whichever precipitates or precipitations are coming out, it should be coherent. What it means, that coherent, I have written one note here. What is the meaning of coherent precipitation? Coherent precipitation means here formation of new phase or the second phase. You can say that new phase or second phase should occur here. Okay, precipitation is nothing but only that solute atom particles will get segregated, or they will come concentrated at one place, and they will form a new phase. And if this condition is satisfying, then and then only age hardening or precipitation hardening phenomenon will occur in that particular alloy. Okay, this is the second condition. First condition is related to the solubility of solute in the solvent. It must decrease with decrease in temperature, or increase with increase in temperature. And second condition is that it should, whichever precipitation particles are separating here due to the precipitation, and it will result in the formation of new phase. Sometimes what will happen, only that alloying element particles will come out. Okay, only that alloying element particle will come out. So it is not satisfying the second conditions, means it does not show the phenomenon of age hardening in the future. So that there are certain examples, like you can say that aluminum and manganese alloy, or aluminum and magnesium alloys are there. They satisfies the first condition, but they are not able to satisfy the second condition. Second condition is that whichever precipitation particles are separating out, that they should have the coherent nature, means they should concentrate at one place. They should concentrate or segregate at the one place, and they should give rise to a new phase. Okay, new phase must be formed due to whichever particles are separating out. If new phase is forming, then and then only they will show the phenomenon of this age hardening or precipitation hardening. This is the second condition. So kindly note down these points. What is the meaning of age hardening, then examples, and the two conditions. I will wait for 2 minutes here. After completing these notes, please put that in the chat box. I will start the next point in this. Okay, please note down this. Okay, can I move towards next point? It is the steps involved in the age hardening or precipitation hardening. If you have completed, I will move towards the next point. Okay, if you have finished the writing of this, I will move towards the next point. And that is the general steps in the age hardening process or precipitation hardening process. Now, whichever steps I am explaining here, these are the steps which are involved in the artificial aging or artificial. Okay, these steps will be involved in the artificial aging process. Means we are doing. Wait for 1 minute. Wait for 1 minute. Okay, my voice is audible, na, clearly. Some disturbance is there. Okay, I will explain it now. Sorry for disturbance. Now, general. Okay, these are general steps in the aging process. Now, you can say that aging process or the age hardening or precipitation hardening process. Now, sometimes in some alloys, natural aging may be there. Means we are not providing any heating there. As time is passing away, automatically its hardness will get improved. That will be termed as the natural aging process. Now, sometimes we are using the artificial aging process, means we are providing the first we will heat that, then after that we will do the cooling, and after that we will provide sometime. Due to that, what will happen, some changes in its microstructure will happen and its hardening will take place. Now, in that artificial aging process, certain treatments or certain steps are there, and three important steps will be there. The first step is the heating step. Okay, first is the heating step. Now, in this heating step, here I have shown you the general diagram. I have considered here general equilibrium diagram for an alloy having element A and B. On this x-axis, weight percentage of element B is there. On an x-axis, temperature I have taken. Now, in the heating process, uh, in the heating process, now you have to first choose the temperature. Particular, you have to do the heating, or this treatment is also known as solutionizing process or homogenization process. Okay. Now what we are doing here, we are going to heat that particular alloy in a particular temperature range so that we will end up with a homogeneous phase. Means single phase solid solution will be there. Single phase solid solution will be there. And how to determine this temperature? This temperature should be in a range where there is only single phase. Now here single phase is in this region. Okay, only alpha phase is there. Then your temperature range should be above this. Means this is your solvus line. Okay, above the solvus line and below this eutectic transformation temperature. This is eutectic transformation temperature line. Below this eutectic temperature and above this solvus line, somewhere here you have to choose that temperature, or you have to take that temperature value. This is the T temperature. Means at that particular temperature, it should have a single phase solid solution. There should be a single phase solid solution. That temperature value you have to select, and you have to uh, you have to hold that alloy at this particular temperature so that only single phase, and that phase should be uniform throughout that alloy, that only the single phase should be there. That's why you have to provide some holding time. This process will be termed as solutionizing or homogenization process. Homogenization means we are getting a single phase throughout that material or throughout that alloy. Single phase is there. Okay, single phase is there, and this we are obtaining by doing the heating above Solvos temperature and below the eutectic temperature, and holding that temperature or holding that alloy at that particular temperature for some specific period of time, so that there will be single phase solid solution. This process will be termed as heating process, or it is also known as solutionizing process, or it is also known as homogenization. Okay, then after performing this first stage, just you can note down the name of this process, that is, write down the heading general steps in edge hardening, and in that process A is heating or solutionizing solutionizing or homogenization. Then the second step is the quenching process, or quenching process is nothing but your what you can say that it is nothing but the cooling. We are rapidly, that whichever alloy we have heated, we are collecting that alloy and we are dipping that directly into the water. This will be termed, we are doing that directly dipping that in the water. Due to this rapid quenching, what will happen, super saturated solid solution will be formed. Now this alloy is in the solution treated condition. Okay, solution treated condition, definitely some increase in the hardness value is there, because we have heated it. Then after heating we have uh, done the holding process for some definite period of time to get the homogeneous phase, and after that we have done the quenching by directly dipping it into the water, and cooling is done up to the room temperature. Now it will show you the increase in the hardness value, but what you have to take a note here, that it hardness is more, but it will be lesser as compared to the annealing process. Okay, in the annealing, the same cooling process, the same cooling process is done in the furnace. Due to some microstructural changes, the hardness value will be more in that slowly cooled condition. How that is happening, that we are going to discuss in the next chapter, where annealing and different high treatment processes are there. Just try to remember that here, as we have done the cooling from the some temperature range, or I will explain here only. Here in this process we have taken temperature below this eutectic temperature or eutectic transformation temperature. In annealing process we are using the higher temperature values. It should be above this line also. Okay, above this line means above this eutectic transformation line, somewhere here we are doing the cooling in the annealing process. That's why hardness value will be different in that case, and in this case hardness value will be different, but definitely the hardness value is more than that of the its actual value before the actual treatment. Now the after this performing this process, the last step will be the aging. Means just you have to wait for the passing of the time. Automatically there will be some increase in the hardness. That process will be termed as the aging process. Now here, this aging, okay, this aging, whichever we have done the first and second step, that will be termed as the artificial aging. First and second step which we have performed, that is the artificial aging process. Means artificial hardening may be there by using these three steps: heating, quenching, and the last step will be aging. And in natural aging, okay, in natural aging process what will happen, we have there is no need to perform heating and quenching process. Just this aging will be there. In this natural aging, just directly we are doing the aging process only. Means just as time is passing away, automatically hardness will get increased. Okay, this is the typical curve here for the natural aging process. Means as time is passing away, automatically its hardness is increasing. This is the natural aging. And in artificial aging, we are using the above conditions. Condition first is heating, then quenching, and after that the aging process will take place. In natural aging, only this direct aging process will be there. In artificial aging, heating, quenching, and then aging will occur. Okay, try to understand the difference. You will get confused that I have written below aging, natural and artificial. Okay, it is not like that. This natural aging means in this process only the third step will be involved, and in artificial aging heating, quenching, and aging. These three steps will be there in the artificial aging. In natural aging, automatically as time is passing away, hardness will get increased. That is the natural aging process. And in artificial aging, we are going to use these three steps: heating, quenching, and then aging process. Means we will, after performing heating and quenching, we will provide some time so that hardness will get increased. That will be the artificial aging. Okay, so these are the different three steps which are involved in the precipitation hardening or age hardening. And after this, the next point is some factors which will influence, okay, factors which will influence the kinetics of the aging process. Okay, kinetics of the aging process. Some factors are there. Before starting these factors, we will see this artificial aging. I have told you that artificial aging, here I have highlighted that artificial aging will be having that three steps. And now in that particular artificial aging, how the temperature is selected, how to select the temperature. Now how to select the temperature, here we are going to select the temperature in such a way that first we will take the temperature difference of room temperature and solutionizing temperature, and whichever value comes, that suppose 600 degrees Celsius temperature is there, difference will be there. That is the room temperature, suppose 23 or 25 degrees Celsius room temperature, and 625 is the solutionizing temperature. Then 600 will be difference between room temperature and solutionizing temperature. Then you have to consider 15 to 25% value, 15 to 25% value of that temperature. Means you can directly consider 25% of 600, it will be 150 degrees Celsius. That temperature you have to select for artificial aging, and you have to do the heating at that particular temperature 150 degrees Celsius, and after that you can do the cooling. Okay, that will be termed as the artificial aging. And here the process, what is the important factor, what is the temperature selection, and how to select the temperature. You have to take the temperature difference of temperature at which you will get the single homogeneous phase throughout that alloy. That will be solutionizing temperature and room temperature. That difference you have to take, and whichever difference value come, for that you have to take the 15 to 25%. You can take 20% or 25% of that value, and that temperature you have to select for doing the means for the heating in the first step, which is our first step. In this way, heating temperature is selected, and after that you have to follow the quenching, and you have to give some time for the aging. That will be the steps. And now here, what you have to take care, that is the over aging you have to avoid. Over aging, sometimes whenever over aging is there, if you provide the more time, then what will happen here, its hardness will get decreased. Now whichever curve of aging, this is the natural aging curve, uh, but in artificial aging this curve will be different. Means it will show you more than one peak values, okay, or maximas will be more. Means some it will increase, then decrease, and again it will increase like this. Okay, like this, some more maximas will be there, and that is due to the presence of some intermediate phases. Due to the existence of the intermediate phases, that will be termed as the GP zone. GP zone means intermediate phases or intermediate precipitation particles will be there, and it is known as GP zone. GP zone is nothing but Gynier Piston zone. Gynier Piston zone, that is the name given. Is Gynier Piston zone, it will be termed as, and sometimes uh, that maximas will occur due to the heterogeneous precipitation also. Okay, heterogeneous precipitation means the rate of the precipitation or rate of that age hardening or precipitation hardening is not same throughout the material or throughout that alloy or whichever solid solution we have formed. Suppose in this here we are forming the solid solution, but whichever rate is there, whichever precipitation rate is there, it whichever alloy here homogeneous solid solution is formed, and at that particular alloy the rate will be different. Rate will be different at that particular form depending on the microstructures. Okay, for clear understanding I should have added some microstructure here. Okay, I will show you that in the next lecture. I will add some microstructures here so that you will understand it. Just what you have to remember, this curve is for natural aging. In artificial aging it should not be it will not be so smooth, which is I have shown here. It will show you more maximas here, only one maxima is here. It will show you more maximas. In artificial aging it curve should be like this. It will go like this, increase then decreases, again increases, like this. Some maximas will be there. Okay, more maximas will be there, and that is due to occurrence of the intermediate phases. That intermediate phases will be termed as GP zones, or Guyonier piston zones, or that maximas are occurring due to precipitation does not occur at the same rate throughout the entire solution. Formation of the precipitation will take place with the different rate. Sometimes it will take very at very faster rate, sometimes it will take at very slow rate. Due to this what will happen, it will be termed as heterogeneous precipitation, and due to this intermediate phases will be formed. Okay, it will trigger this heterogeneous precipitation will trigger the formation of GP zone. Okay, due to this what will happen, that reality in aging curve will be not so smooth, which is shown in this diagram. It will show you more maximas. Okay, more maximas will be there. That will be the difference in the natural aging curve and artificial aging curve. Okay, so these are the different steps in the age hardening. Then after these stages there are certain factors which will affect the kinetics of the aging process. Kinetics is nothing but the you can say that speed of that aging process. Okay, speed or time required for that aging process. Certain four factors are there. Out of that four factors, the first factor is the temperature of aging. Now here uh, whichever factor I have selected, temperature here I have selected, what will be the effect of that temperature on that aging curve that I have shown here. Effect of aging temperature on the values of the hardness. Okay. What will happen on the hardness of that particular alloy if I selected different temperature zones? Okay, different temperature values here, T1, T2, T3, and this T3 is greater than T2, T2 is greater than T1. Okay, means what will happen here, if you observe that the peak hardness values, this will be the peak hardness values, peak hardness values, and time required to reach this peak hardness value. This will be on x-axis, you will get the time, and this is the hardness. Okay, now here you can clearly see that the peak hardness and the time to reach the peak hardness, both values decreases with increasing temperature of aging. Are you getting this? Peak hardness value as well as time required to reach the peak hardness value. Suppose for this T3 temperature, this is the maximum temperature, peak hardness value is lesser. Okay, peak hardness value, hardness maximum hardness obtained is less in this T3, and time required is also less. Then in this T2 it will take little bit more time, and it will also provide you little bit more hardness. And this T1 it will give you more hardness, but it will take more time. It will take more time. In short, the peak hardness and the time to reach the peak hardness. Okay, peak hardness value and time to reach that peak hardness value both will decrease as temperature increases. Okay, Peak hardness is also decreasing. Here peak hardness is more for this T1. As temperature is increasing, peak hardness values will drop, and along with that, time required to reach that peak hardness value will also drop. This is the effect of the temperature on the aging. Okay, this is the first point, effect of the temperature on the aging. Then next is the cold working process. Cold working process. Now here I have shown the three curves. Same curves will be there. That is, on x-axis time will be there, on y-axis hardness will be there. We will plot this aging curve. This will be the aging curve, and this curve I have plotted three curves here, A, B, C. Now A curve will be without cold working, B will be with intermediate cold working, and C will be very high degree of cold working. Now as you can clearly see that if there is no cold working, then its hardness value is less and it will take more time for aging. Okay, without cold working, hardness value is less and it will take more time. For second curve, you can see that if suppose very slight cold working is done on that alloy, then what will happen? It will provide you the more peak hardness value. This is the peak hardness value for that particular alloy or for that particular curve. It will show you the more peak hardness value with lesser possible time. Okay, lesser possible time. And if cold working degree or cold working operation you have performed heavily or with high degree, then it will show you higher values of the peak hardness with lesser time. Okay, in short you can say that whenever cold working operation is done, or whenever cold working of that solid solution is done, whenever cold working of that solid solution is done, it will show you the more hardness with the lesser possible time. Okay, this will be the second factor, that is the cold working of the solid solution. Then the third factor, that is the alloy composition. Alloy composition. Now in this alloy composition, what here, here I have taken the three curves. You can see here alloys, alloy first A, alloy composition which is having composition less than the solubility limit. Okay, there will be certain solubility limit of the solute in the solvent, that is alloying element in the base metal. I have taken one alloy with the less composition than its solubility limit. Then after that I have taken the second B sample with the alloy, alloying element percentage very near to its solubility limit. And in the third composition I have taken an alloy having alloying element content more than its solubility limit. And because I will get this result, and here you can clearly see that whenever, this is the first curve, whenever percentage of the alloying element is less than its solubility limit, very less than its solubility limit, then it will show you the lesser hardness and it will take more time for the aging. This first curve. Then the second curve, here I have taken the solubility limit or alloying element percentage is very nearer to the solubility limit. Then it will show you the more hardness or highest hardness will be observed here, and with the least possible aging time. Okay, higher hardness with the least possible aging time, it can be obtained by taking a alloy composition, and alloying element percentage should be very nearer to its solubility limit. Okay, very nearer to the solubility limit means single phase will be there. Why it is happening? Because there will be single phase, and due to that single phase it will give you the more hardness after the cooling. Okay, that will be observed in the composition when you are taking alloy with the composition very nearer to its solubility limit. And when you have taken the alloy, this third curve, the C curve, alloy composition more than solubility limit, then it will give rise to the intermediate phases. And due to that formation of intermediate phases, what will happen? Its hardness values will fall, and it will take more time for aging. Okay, in short, whenever alloying element percentage is less than the solubility limit or very high than the solubility limit, then it will show you lesser hardness and with more aging time. And whenever alloying element percentage in that particular alloy is very near to solubility limit, it will show you the more hardness, peak hardness value will be more, and it will require less time for aging, very less time. High hardness and with less time can be obtained by taking the alloying element percentage very near to the solubility limit. So this is the third factor which will trigger the aging process, or which will affect the kinetics of the aging process. And this is the last point, fourth point, impurities, and you can say that homogeneity of the particular alloy here. This point is explained by taking the composition. Okay, aluminum and copper alloy, here I have taken 4.5% copper and remaining will be aluminum. Here 4.5% copper, 0.6% iron, and remaining will be aluminum. Here I have taken the aluminum copper alloy and its hardness value. Brinell hardness is nothing but this hardness tester is used for measuring the hardness values. Okay, now here effect of iron and copper on the hardening process or hardening response from that aluminum copper alloy is explained here. Now you can clearly understand from the different curves here, whenever alloying element or single alloying element is there, aluminum with 4.5% copper, then it will show you, check here, it will show you more hardness values. More hardness value is obtained here as far as it is having lesser impurities, or other alloying elements are in lesser amount. Okay, and homogeneity will also, as I will explain it in the two ways. You can observe these three curves which are shown by the continuous line: 1.5% copper, 3% copper, and 4.5% copper. This will show you the homogeneity concept. Means you can say that here only copper is there but its hardness is less. But as its value amount is increasing, its amount is increasing means it will be very nearer to solubility limit. Whenever it is lesser than the solubility limit, its hardness will be less. 1.5 hardness will be less. It is then moved to the little bit closer to that solubility limit, then hardness slightly increases. And when it moves to the 4.5% copper, that is nearer to the solubility limit, means it will show you the homogeneous solid solution. Homogeneous solid solution will be formed there at the higher temperature ranges. Due to that, after cooling, it will show you the more hardness. More homogeneous will be there, or nearer to the solubility limit. Its alloying element percentage is nearer to the solubility limit. It will show you the more homogeneous structure. Due to that, it's having higher hardness value. And when in this more homogeneous structure or composition, you can say that when amount of other impurities is increasing, suppose iron 0.6% iron is added, then its hardness will fall. And if this iron is again amount of iron is increased in this same homogeneous composition, then what will happen? Suppose 1% iron is added, then again you can observe these two dotted curve. Your hardness is more, it will fall due to increase in this iron percentage. This iron will act as impurity here. Okay, so in this way, the effect of impurities and homogeneities will be there on the kinetics of that aging process or the speed of that aging process. I will repeat this part again. When it is more homogeneous, it is more homogeneous means its solubility, it should be closer to the solubility limit. Composition should be closer to the solubility limit, then it will show you the more hardness. For example, 4.5% copper alloy will show you more hardness as compared to the aluminum copper alloys having 1.5 and 3% copper, due to the more homogeneous structure or more homogeneous phase will be obtained here. This is related to the homogeneity point. Then impurity point, as impurity goes on increasing in this homogeneous structure, its hardness will decrease. Suppose you have added 0.6% iron, hardness will fall. then 1% iron, again hardness will fall. In this way it will, this homogeneity and impurity will affect the kinetics of that aging process or time required for that aging process. Okay, in this way these are the four factors which will influence the kinetics of aging. In this way we have completed this point, that is age hardening process or precipitation hardening process. Now I will summarize in the short way. Okay, we have started with the concept of age hardening. What is the meaning of age hardening or precipitation hardening? Then after that, few examples we have discussed. Then conditions to satisfy or to for the occurrence of that age hardening process in the particular alloy system. Two conditions are there. And after that, we have discussed the general steps in the age hardening process. Three steps are there: heating, quenching, and aging. Heating is also termed as this solutionizing or homogenization, and quenching and aging. Then we have discussed the uh, what exactly happens in the artificial aging, how to select the temperature range, then why that natural aging curve and artificial aging curves are having difference, or more maximas will be there in the artificial aging due to appearance of this GP zone, that is Guyner-Priston zone. And this Guyner-Priston zone may occur due to heterogeneous precipitation also. Heterogeneous precipitation automatically results in the formation of that GP zone. And then the factors influencing the kinetics or speed of that aging process, four factors: temperature of aging, then cold working of the solid solution, then alloy composition, and the last is the impurity and homogeneity of that alloy. These four factors will affect that aging process. Okay. Now, in short, this GP zone is nothing but the intermediate phases that you have to remember, and the Preston zone. In this way, we have completed this point, that is the age hardening or precipitation hardening, and different steps involved in that age hardening and precipitation hardening, along with the conditions and factors affecting the kinetics of the aging process. Okay. Okay. Thank you for attending this session.